So in the last video, I left you with a cliffhanger. I introduced you to the minimum cut problem. I introduced you to a very simple and elegant randomized algorithm in the form of the contraction algorithm. We observed that sometimes it finds a min cut and sometimes it doesn't. And so the $64,000 question is just how frequently does it succeed and just how frequently does it fail. So now that hopefully you've brushed up on your conditional probability and independence, we're going to give a very precise answer to that question in this lecture. So recall on this problem we're given as input an undirected graph, possibly with parallel edges, and the goal is to compute among the exponential number of possible different cuts, that with the fewest number of crossing edges. So for example, in this graph here, which you've seen in a previous video, the goal is to compute the cut AB here, because there are only two crossing edges, and that's as small as it gets. That's the minimum cut problem, and Karger proposed the following random contraction algorithm based on random sampling. So we have n-2 iterations, and the number of vertices gets decremented by 1 in each iteration. So we start with n vertices, we get down to 2. And how do we decrease the number of vertices? We do it by contracting or fusing two vertices together. How do we pick which pair of edges, which pair of vertices to fuse? Well, we pick one of the remaining edges uniformly at random. So there's however many edges there are remaining, we pick each one equally likely. If the endpoints of that edge are u and v, then we collapse u and v together into a single supernode. So that's what we mean by contracting two nodes into a single vertex. And then if that causes any self-loops, and as we saw in the examples, we will in general have self-loops, then we delete them before proceeding. After the n-2 iterations, only two vertices remain. You'll recall that those two vertices naturally correspond to a cut. The first group of the cut A corresponds to the vertices that were fused into one of the super vertices remaining at the end. The other super vertex corresponds to the set B, the other original vertices of the graph. So the goal of this video is to give an answer to the following question: what is the probability of success? Whereas by success we mean outputs particular min cut A comma B. So let's set up the basic notation. We're going to fix any old input graph, undirected graph. And as usual, we use n to denote the number of vertices and m to denote the number of edges. We're also going to fix a minimum cut A comma B. If a graph has only one minimum cut, then it's clear what I'm talking about here. If a graph has multiple minimum cuts, I'm actually selecting just one of them. Okay, so I'm going to focus on a distinguished minimum cut A comma B, and we're only going to define the algorithm as successful if it outputs this particular minimum cut AB. If it outputs some other minimum cut, we don't count it. We don't count it as successful. Okay, so we really want this distinguished minimum cut A comma B. In addition to n and m, we're going to have a parameter k, which is the size of the minimum cut. That is, it's the number of crossing edges of a minimum cut, for example, that cross A comma B. The k edges that cross the minimum cut AB we're going to call capital F. So the picture you want to have in mind is there is out there in the world this minimum cut AB. There's lots of edges with both endpoints in A, lots of edges possibly with both endpoints in B, but there's not a whole lot of edges with one endpoint in A and one endpoint in B. So the edges F would be precisely these three crossing edges here. So our next step is to get a very clear understanding of exactly when the execution of the contraction algorithm can go wrong and exactly when it's going to work, exactly when we're going to succeed. So let me redraw the same picture from the previous slide. So given that we're hoping that the contraction algorithm outputs this cut AB at the end of the day, what could possibly go wrong? Well, to see what could go wrong, suppose at some iteration, one of the edges in capital F, remember F are the edges crossing the min cut AB, so it's these three magenta edges in the picture. Suppose at some iteration one of the edges of F gets chosen for contraction. Well, because this edge of F has one endpoint in A and one endpoint in B, when it gets chosen for contraction, it causes this node from A and this node from B to be fused together. What does that mean? That means in the cut that the contraction algorithm finally outputs, this node from A and this node from B will be in the same side of the output cut. Okay, so the cut output by the contraction algorithm will have on one side both the node from A and a node from B. Therefore, the output of the contraction algorithm, if this happens, will be a different cut than AB. Okay, it will not output AB if some edge of f is contracted. And if you think about it, the converse is also true. So let's assume now that in each of the n-2 iterations, the contraction algorithm never contracts an edge from capital F. Remember, capital F are exactly the edges with one endpoint in A and one endpoint in B. So if it never contracts any edge of F, then it only contracts edges where both endpoints lie in capital A or both endpoints lie in capital B. Well, if this is the case, then vertices from A always stick together in fused nodes, and vertices from B always stick together in the fused nodes. There is never an iteration where a node from A and a node from B are fused together. What does that mean? That means that when the algorithm outputs a cut, all of the nodes in A have been grouped together, all of the nodes in B have been grouped together in each of the two supernodes, which means that the output of the algorithm is indeed the desired min cut A, B. Summarizing, the contraction algorithm will do what we want. It will succeed and output the cut A, B if and only if it never chooses an edge from capital F for contraction. Therefore, the probability of success, that is the probability that the output is the distinguished min cut A, B, is exactly the probability that it never contracts an edge of capital F. So this is what we're going to be interested in here. This will be the object of our mathematical analysis. The probability that in all of the n-2 iterations we never contract an edge of capital F. So to think about that, let's think about each iteration in isolation and actually define some events describing that. So for an iteration I, let Si denote the event that we screw up in iteration I. With this notation, we can succinctly say what our goal is. So to compute the probability of success, what we want to do is we want to compute the probability that none of the events S1, S2 up to Sn-2 ever occur. So I'm going to use this not symbol to say that S1 does not happen. So we don't screw up in iteration 1, we don't screw up in iteration 2, we don't screw up in iteration 3, and so on, all the way up to we don't screw up, we don't contract anything from capital F in the final iteration either. So summarizing, analyzing the success probability of the contraction algorithm boils down to analyzing the probability of this event, the intersection of all of the not SIs with I ranging from iteration 1 to iteration n-2. So we're going to take this in baby steps, and the next quiz will lead you through the first one, which is let's have a more modest goal. Let's just think about iteration number 1. Let's try and understand what's the chance we screw up, what's the chance we don't screw up just in the first iteration. So the answer to this quiz is the second option. The probability is k over m, where k is the number of edges crossing the cut A, B, and m is the total number of edges. And that's just because the probability of S1, probability that we screw up, is just the number of crossing edges. That's the number of outcomes which are bad, which trigger S1, divided by the number of edges. That's the total number of things that could happen. And since all edges are equally likely, it just boils down to this. And by the definition of our notation, this is exactly k over m. So this gives us an exact calculation of the failure probability in the first iteration as a function of the number of crossing edges and the number of overall edges. Now it turns out it's going to be more useful for us to have a bound, not quite as exact, an inequality, that's in terms of the number of vertices n rather than the number of edges m. The reason for that is it's a little hard to understand how the number of edges is changing in each iteration. It's certainly going down by 1 each iteration because we contract an edge each iteration, but it might go down by more than 1 when we delete self-loops. By contrast, the number of vertices is this very steady, obvious process. One less vertex with each successive iteration. So let's rewrite this bound in terms of the number of vertices n. To do that in a useful way, we make the following key observation. I claim that in the original graph G that we were given as input, every vertex has at least k edges incident on it. That is, in graph theoretic terminology, every edge has degree at least k. Where, recall, k is the number of edges crossing our favorite min cut A, B. So why is that true? Why must every vertex have a decent number of neighbors, a decent number of edges incident to it? Well, it's because if you think about it, each vertex defines a cut by itself. Remember, a cut is just any grouping of the vertices into two groups that are non-empty, that don't overlap. So one cut is to take a single vertex and make that the first group A, and take the other n-1 vertices and make that the second group, capital B. So how many edges cross this cut? Well, it's exactly the edges that are incident on the first node, on the node on the left side. So if every single cut, if all exponentially many cuts have at least k crossing edges, then certainly the n cuts defined by single vertices have at least k crossing edges, so therefore the degree of every vertex is at least k. So our assumption that every single cut in the graph has at least k crossing edges gives us a lower bound on the number of edges incident on each possible vertex. So why is that useful? Well, let's recall the following general fact about any graph, which is that if you sum up over the degrees of the nodes, so if you go node by node, look at how many edges are incident on that node, that's the degree of v, and then sum them up over all n vertices, what do you get? You get exactly twice the number of edges. Okay, so this is true for any undirected graph, that the sum of the degrees of the vertices is exactly double the number of edges. To see this, you might think about taking a graph, starting with the empty set of edges, and then adding the edges of the graph one at a time. Each time you add a new edge to a graph, obviously the number of edges goes up by 1, and the degree of each of the endpoints of that edge also go up by 1. And there are, of course, 2 endpoints. So every time you add an edge, the number of edges goes up by 1, the sum of the degrees goes up by 2. Therefore, when you've added all the edges, the sum of the degrees is double the number of edges that you've added. That's why this is true. Now, in this graph that we have at hand here, every degree is at least k, and there's n nodes. So this left-hand side, of course, is at least kn for us. So therefore, if we just divide through by 2 and flip the inequality around, we have the number of edges has to be at least the size of the crossing cut, or the degree of every vertex, times the number of vertices divided by 2. So this is just the previous inequality rearranging. Putting this together with your answer on the quiz, since the probability of S1 is exactly k over m, and m is at least kn over 2, if we substitute, we get that the probability of S1 is, at worst, 2 over n, 2 over the number of vertices, and the k cancels out. So that's sort of our first milestone. We've figured out the chance that we screw up in the first iteration, that we pick some edge from that crosses the cut AB, and things look good. This is a small number, right? So in general, the number of vertices might be quite big, and this says that the probability we screw up is only 2 over the number of vertices. So far, so good. Of course, this was only the first iteration. Who knows what happens later? So now that we understand the chances of screwing up in the first iteration, let's take our next baby step and understand the probability that we don't screw up in either of the first 2 iterations. That is, we're going to be interested in the following probability: the probability that we don't screw up in the first iteration nor in the second iteration. Now, you should go back to the definition of a conditional probability to realize that we can rewrite an intersection like this in terms of conditional probabilities, namely as the probability that we don't screw up in the second iteration, given that we didn't do it already, times the probability that we didn't screw up in the first iteration. Okay, so the probability that we miss all of these k vulnerable edges in the second iteration, given that we didn't contract any of them in the first iteration. Now, notice this we already have a good understanding of. On the previous slide, we gave a nice lower bound of this. We said there's a good chance that we don't screw up, probability at least 1 minus 2 to the n. And in some sense, we also have a very good understanding of this probability. We know this is 1 minus the chance that we do screw up. And what's the chance that we do screw up? Well, these k edges are still hanging out in the graph. Remember, we didn't contract any in the first iteration. That's what's given. So there are k ways to screw up. And we choose an edge to contract uniformly at random. So the total number of choices is the number of remaining edges. Now the problem is, what's nice is we have an exact understanding of this probability. This is an equality. The problem is we don't have a good understanding of this denominator. How many remaining edges are there? We have an upper bound on this. We know this is at most m minus 1. We certainly got rid of one edge in the previous iteration, but actually, if you think about it, what we need on this quantity is a lower bound. And that's a little unclear because in addition to contracting the one edge and getting that out of the graph, we might have created a bunch of self loops and deleted all of them. So it's hard to understand exactly what this quantity is. So instead, we're going to rewrite this bounded in terms of the number of remaining vertices. And of course, we know there's exactly n minus 1 vertices remaining. We took 2 in the last iteration, we contracted it down to 1. So how do we relate the number of edges to the number of vertices? Well, we do it just in exactly the same way as in the first iteration. We make a sort of more general observation. For the first iteration, we observe that every node in the original graph induces a cut. Okay, with that node on one side, the other n minus 1 edges on the other side. But in fact, that's a more general statement. Even after we've done a bunch of contractions, any single node in the contracted graph, even if it represents a union of a bunch of nodes in the original graph, we can still think of that as a cut in the original graph. Right? So if there's some supernode in the contracted graph, which is the result of fusing 12 different things together, that corresponds to a cut where those 12 nodes in the original graph are the one side A, and the other n minus 12 vertices are the other side of the cut B. Okay, so even after contractions, as long as we have at least 2 nodes left in our contracted graph, you can take any node and think of it as half of a cut, one side of a cut in the original graph. Now remember, k is the number of edges crossing our minimum cut, a comma b, so any cut in the original graph G has to have at least k crossing edges. So, since every node in the contracted graph naturally maps over to a cut in the original graph with at least k edges crossing it, that means that in the contracted graph all of the degrees have to be at least k. If you ever had a node in the contracted graph that had only, say, k minus 1 incident edges, well then you'd have a cut in the original graph with only k minus 1 edges, a contradiction. So just like in the first iteration, now that we have a lower bound on the degree of every single vertex, we can derive a lower bound on the number of edges that remain in the graph. The number of remaining edges is at least 1/2, that's because when you sum over the degrees of the vertices, you double count the edges, times the degree of each vertex, and we just argued that that's at least k in this contracted graph, times the number of vertices, and we know there's exactly n minus vertices left in the graph at this point. So now what we do is we plug this inequality, we plug this lower bound on the number of remaining edges on as in, we substitute that for this denominator. So in lower bounding the denominator, we upper bound this fraction, which gives us a lower bound on 1 minus that fraction, and that's what we want. So what we find is that the probability that we don't screw up in the second iteration, given that we didn't screw up in the first iteration, where again by screwing up means picking one of these k edges crossing AB to contract, is at least 1 minus 2 over n minus 1. So that's pretty cool. We took the first iteration, we analyzed it, we showed the probability that we screw up is pretty low. We succeed with probability at least 1 minus 2 over n. In the second iteration, our success probability has dropped a little bit, but it's still looking pretty good for reasonable values of n. 1 minus 2 over n minus 1. Now, as I hope you've picked up, we can generalize this pattern to any number of iterations. So the degree of every node in the contracted graph remains at least k. The only thing which is changing is the number of vertices is dropping by 1. So extending this pattern to its logical conclusion, we get the following lower bound on the probability that the contraction algorithm succeeds. So the probability that the contraction algorithm outputs the cut AB, you'll recall we argued, is exactly the same thing as the probability that it doesn't contract anything, any of the k crossing edges, any of the set F in the first iteration, nor in the second iteration, nor in the third iteration, and so on, all the way up to the final n minus 2th iteration. Using the definition of conditional probabilities, this is just the probability that we don't screw up in the first iteration times the probability that we don't screw up in the second iteration, given that we didn't screw up in the first iteration, and so on. In the previous 2 slides, we showed that we don't screw up in the first iteration with probably at least 1 minus 2 over n, in the second iteration with probably at least 1 minus 2 over n minus 1, and of course you can guess what that pattern looks like, and that results in the following product. Now because we stop when we get down to 2 nodes remaining, the last iteration in which we actually make a contraction there are 3 nodes, and in the second to last iteration in which we make a contraction there are 4 nodes. So that's where these last two terms come from. Rewriting, this is just n minus 2 over n times n minus 3 over n minus 1, and so on. And now something very cool happens, which is massive cancellation. And to this day, this is always just incredibly satisfying to be able to cross out so many terms. So you get n minus 2 crossing out here. It's going to be a pair of n minus 3s that get crossed out, n minus 4s, and so on. On the other side, there's going to be a pair of 4s that get crossed out, and a pair of 3s that get crossed out. And we'll be left with only the two largest terms on the denominator and the two smallest terms in the numerator, which is exactly 2 over n times n minus 1. And to keep things simple, among friends, let's just be sloppy and lower bound this by 1 over n squared. So that's it. That's our analysis of the success probability of Karger's contraction algorithm. Pretty cool, pretty slick, huh? Okay, I'll concede, probably you're thinking, hey, wait a minute. We're analyzing the probability that the algorithm succeeds, and we're thinking of the number of vertices n as being big. So what we see here is a success probability of only 1 over n squared, and that kind of sucks. So that's a good point. Let me address that. Problem. This is a low success probability. So that's disappointing. So why are we talking about this algorithm or this analysis? Well, here's something I want to point out. Maybe this is not so good. 1 in n squared, you're going to succeed. But this is still actually shockingly high for an oblivious algorithm, which honestly seems to be doing almost nothing. This is a non-trivial lower bound, a non-trivial success probability, because, don't forget, there's an exponential number of cuts in the graph. So if you try to just pick a random cut, i.e. you put every vertex 50-50 left or right, you'd be doing way worse than this. You'd have a success probability of like 1 over 2 to the n. So this is way, way better than that. And the fact that it's an inverse polynomial means that using repeated trials, we can turn a success probability that's incredibly small into a failure probability that's incredibly small. So let me show you how to do that next. So we're going to boost the success probability of the contraction algorithm in, if you think about it, a totally obvious way. We're going to run it a bunch of times, each one independently, using a fresh batch of random coins. And we're just going to remember the smallest cut that we ever see. And that's what we're going to return, the best of a bunch of repeated trials. Now the question is, how many trials are we going to need before we're pretty confident that we actually find the min cut we're looking for? To answer this question rigorously, let's define some suitable events. So by TI, I mean the event that the ith trial succeeds. That is, the ith time that we run the contraction algorithm, it does output the desired min cut A, B. For those of you that watched the part 2 of the probability review, I said a rule of thumb for dealing with independence is that you should maybe, as a working hypothesis, assume random variables are dependent unless they're explicitly constructed to be independent. So here's a case where we're just going to define the random variables to be independent. We're just going to say that we run the contraction algorithm over and over again with fresh randomness. So they're going to be independent trials. Now we know that the probability that a single trial fails could be pretty big. Could be as big as 1 minus 1 over n squared. But here now with repeated trials, we're only in trouble if every single trial fails. If even one succeeds, then we find a min cut. So a different way of saying that is we're interested in the intersection of T1 and T2 and so on. That's the event that every single trial fails. And now we use the fact that the trials are independent. So the probability that all of these things happen is just the product of the relevant probabilities. So the product from I equal 1 to capital N of the probability of not TI. Recall that we argued that the success probability of a single trial was bounded below by 1 over n squared. So the failure probability is bounded above by 1 minus 1 over n squared. So since that's true for each of the capital N terms, we get an overall failure probability for all capital N trials of 1 minus 1 over little n squared raised to the capital N. All right, so that's a little calculation. Don't lose sight of why we're doing the calculation. We want to answer this question. How many trials do we need? How big does capital N need to be before we are confident that we get the answer that we want? Well, to answer that question, I need a quick calculus fact, which is both very simple and very useful. So for all real numbers x, we have the following inequality. 1 plus x is bounded above by e to the x. So I'll just give you a quick proof by a picture. So first think about the line 1 plus x. What does that cross through? Well, that crosses through the points when x is minus 1, y is 0, and when x is 0, y is 1. And it's a line, so this looks like this blue line here. What does e to the x look like? Well, if you substitute x equals 0, it's going to be 1. So in fact, the two curves kiss each other at x equals 0. But exponentials grow really quickly. So as you jack up x to higher positive numbers, it becomes very, very steep. And for x negative numbers, it stays non-negative the whole way. So this sort of flattens out for the negative numbers. So pictorially, and I encourage you to type this into your own favorite graphing program, you see that e to the x bounds above everywhere the line 1 plus x. For those of you that want something more rigorous, there's a bunch of ways to do it. For example, you can look at the Taylor expansion of e to the x at the point 0. What's the point? The point is this allows us to do some very simple calculations on our previous upper bound on the failure probability by working with exponentials instead of working with these ugly 1 minus whatever is raised to the whatever term. So let's combine our upper bound from the previous slide with the upper bound provided by the calculus fact. And to be concrete, let's substitute some particular number of capital N. So let's use little n squared trials, where little n is the number of vertices of the graph. In which case, the probability that every single trial fails to recover the cut a comma b is bounded above by e to the minus 1 over n squared. That's using the calculus fact applied with x equal to minus 1 over n squared. And then we inherit the capital N in the exponent, which we just instantiated to little n squared. So of course the n squareds are going to cancel. This is going to give us e to the minus 1, also known as 1 over e. So if we're willing to do little n squared trials, then our failure probability has gone from something very close to 1 to something which is more like, say, 30 some odd %. Now, once you get to a constant success probability, it's very easy to boost it further by just doing a few more trials. So if we just add a natural log factor, so instead of little n squared trials, we do little n squared times the natural log of little n. Now the probability that everything fails is bounded above by the 1 over e that we had last time, but still with a residual natural log of n up top, and this is now merely 1 over n. So I hope it's clear what happened. We took a very simple, very elegant algorithm that almost always didn't do what we want. It almost always failed to output the cut AB. It did it with only probability 1 over little n squared. But 1 over little n squared is still big enough that we can boost it so that it almost always succeeds just by doing repeated trials. And the number of repeated trials that we need is the reciprocal of its original success probability boosted by a further logarithmic factor. So that transformed this almost always failing algorithm into an almost always succeeding algorithm. And that's a more general lesson, more general algorithmic technique, which is certainly worth remembering. Let me conclude with a couple comments about the running time. This is probably the first algorithm of the course where we haven't obsessed over just what the running time is. Now that said, it's simple enough, it's not hard to figure out what it is, but it's actually not that impressive, and that's why I haven't been obsessing over it. This is not almost linear. This is not a for-free primitive as I've described it here. So it's certainly a polynomial time algorithm. Its running time is bounded above by some polynomial in n and m, so that's way better than the exponential time you'd get from brute force search through all 2 to the n possible cuts. But it is certainly, the way I've described it, you've got to do n squared trials plus a log factor, which I'm not even going to bother writing down. And also, each trial, well, at the very least, you look at all the edges, so that's going to be another factor of m. So this is a bigger polynomial than in almost any of the algorithms that we're going to see. Now, I don't want to undersell this application of random sampling to computing cuts, because I've just shown you the simplest, most elegant, most basic, but therefore also the slowest implementation of using contractions to compute cuts. There's been follow-up work with a lot of extra optimizations, in particular doing stuff much more clever than just repeated trials. So basically using work that you did in previous trials to inform how you look for cuts in subsequent trials, and you can shave large factors off of the running time. So there are much better implementations of this randomized contraction algorithm than the one I'm showing you here. Those are, however, outside the scope of this course.